Good morning, my wonderful people. Welcome back to Civil Tech, where we solve strength of material. So guys, here we have the name of this search or search to calculate. It's a calculate the support reactions and A and B. So guys, today we are going to solve this B. We are going to calculate the reaction support at point A and the reaction support at point B. At point A, it is simple supported, and at point B, it is articulated. We have two concentrated loads, F1 which is equal to 20 kN and F2 equals to 40 kN. And here we have a uniformly distributed load. It is uniformly distributed at this our distance 3 meters. B is equal to 30 kN per meter length. So the first thing they are asking us to do is to calculate the reaction support. So to calculate the reaction support, the first thing we need to do is we need to isolate this our B. So we start with the isolation. So like we said, we first of all need to isolate our bar. This is the B. Simple support we have here and A. We have the two concentrated load, F1 and F2. F2, F1. Here we have 20 kN. Here for the F2 we have our 40 kN. And we have the uniformly distributed load. Now we need to convert this uniformly distributed load to a point load. Now to convert this uniformly distributed load to a point load, what we need to do is we need to take this our uniformly distributed value of this our uniformly distributed load, multiply it by the total distance it covers because it is per meter length. So we are going to take 30 kN per meter length times 3. It will give us 90. My guys, come back up. So we are going to have 90 kN. So guys, here we have our RA. We have the force F1 equals to 20 kN. We have F2 equals to 40 kN. We have P. We have now converted this our uniformly distributed load to a point load. It has given us 40. It is 90 kN. So we have 90 kN. So guys, don't forget there's a space between F2 and the beginning of this our uniform. So guys, this is the isolation of this our B. This is the F1 equals to 20 kN, F2 equals to 40 kN, and P. We have converted this our uniformly distributed load to a point load by taking the force 80 kN per meter length, we multiply it by 3 meters. The total length we have multiplied are together. So 30 times 3 is 90 kN per meter length. Now, to put it as a point load, we need to divide this our 3 meters into 2. So we are going to have 1.5 meters and 1.5 meters. So this is our isolation, this is our A, and this is our B. Don't forget at point B it is articulated. It means it has an X component and a Y component. So at point B it has an X component and a Y component. So this is the X component. We are going to have RB X, and here we are going to have RB Y. So the first thing we are going to do is we are going to state the principle of statics. Statics states that for a body to be in equilibrium, the sum of all the forces acting on that body must be equal to 0. So sum of external forces must be equal to 0. minus F1 minus F2 minus P plus arrow B equal to 0. So we are going to have arrow A plus arrow B is equals to F1 plus F2 plus F plus P. Right? So we are going to have arrow A plus arrow B is equal to, the value for our F1 there is 20, the value for F2 is 40, so this is 60. 60 plus 90, we have 150. So we have 150 kilonewton. This is our equation 1. We have one equation 2 unknown, we cannot move further to solve. So what we need to do is we apply the second principle of statistics, which states that sum of moment of external forces acting on this body must be equal to 0. So sum of moment of external forces must be equal to 0 about a certain particular point. About a certain point. And we know that by definition, moment is the product of the force by the perpendicular distance or the lever arm. So I have chosen point A to be my center of moment. So the moment of arrow A about point A is 0. The moment of F1 about point A is negative F1 into the perpendicular distance. F1 is the force. And now we need to look for the perpendicular distance from F1 to our center of moment. This is our center of moment. So we are going to have F1 into 2. Same for F2, we are going to have negative F2 into 4. It is 4 because we are summing the perpendicular distance from F2 to our center of moment, taking 2 meters plus 2 meters giving us 4 meters. That's why we have 4 here. Same for P. We are going to have negative P. Negative P into, this is 6. This is 6, 7.5 into 7.5. Now the moment of arrow B Y. The moment of arrow BX is 0. Why? Because the line of action of arrow BX passes through our center of moment. But the moment of arrow BY is not 0. The moment of arrow BY will be, this is 3 plus 6, 9. We are now going to have plus arrow B into 9 equal to 0. So the value for F1 here is 20. So I'm going to have 40. So negative 40 minus 4 times 4 is 16. 160 minus 90 times 7.5. So 90 times 7.5, we have 675 plus 9 arrow B equal to 0. Now we have 9, we make arrow B the subject of our equation is equal to, so it's equal to 875. So our arrow B will be equal to 875 divided by 9. So therefore, our arrow B will be equal to 875 divided by 9. So we are going to have 97.22 kilonewton. So this is the value for our arrow B, 97.22 kilonewton. Now let's calculate the value for our arrow A. Knowing that we take our first equation that we had from the beginning, arrow A plus arrow B is equal to 150 kilonewton. Arrow A plus arrow B is equal to 150 kilonewton. This was our equation 1. Now we have the value for arrow B, we are looking for arrow A, so we make arrow A the subject of the equation. Minus arrow B. So arrow A is equal to 150 minus 90. We are going to have 52. We are going to have 52.78 kilonewton. So this is the value of our RA. This is the value for our RA. Looking at this big logically, we discover the answer for RA and RB seems to be true. Because at RB, at the point RB, you carry more load than RA.